Hi, welcome back to recitation. We've been talking about antidifferentiation or integration by substitution and also by a method that Professor Jerrison called advanced guessing. So I have a few problems up on the board behind me, three antiderivatives for you to compute. So the first one is e to the 2x times cosine of the quantity 1 minus e to the 2x dx. The second one is 4x times the quantity 5x squared minus 1 raised to the 1/3 power. And the third one is tan of x dx. So why don't you spend a few minutes, try and compute those antiderivatives yourself, come back, and we can see how you did. All right, so welcome back. We have these three antiderivatives, so let's take them in order. So this first one that I wrote is the antiderivative of e to the 2x times cosine of the quantity 1 minus e to the 2x dx. So this problem seems to me like a good candidate for a substitution. So we have this clear sort of nested function thing going on. We have cosine of 1 minus e to the 2x. And then out front, we have something that looks a lot like the derivative of this 1 minus e to the 2x. So I'm going to try this with substitution then. And I think there are a few choices of substitution. But a natural one is to sort of find the most complicated inside piece. So in this case, that's this whole thing 1 minus e to the 2x. So I'm going to take, for my substitution, I'm going to take u equals 1 minus e to the 2x. And so that means du is equal to minus 2 e to the 2x dx. OK, so that's my substitution. And when I put my substitution into this integral, what do I get? Well, so I have cosine of 1 minus e to the 2x just becomes cosine of u. Now, e to the 2x dx, that's very, very close to this du here. So what's different is that here I have a minus 2. So actually, e to the 2x dx is du divided by minus 2. So this is cosine u times du divided by minus 2. Now, another way to get to this point is you could solve this equation for dx and substitute it in, and also solve this equation for e to the 2x and substitute it in, and things should work out more or less the same if you try that out. So actually, you won't even need to make that second substitution. You'll just get some nice cancellation there. It's even simpler than what I just said. OK, so we do this antiderivative. We've made the substitution. So now we have just the antiderivative of a cosine function. All right, well, that's not that bad, because we know that the derivative of sine is cosine. So the antiderivative of cosine is sine. So this is equal to, so that minus 2, that 1 over minus 2 is just going to stick around. So it's 1 over minus 2 sine of u, plus a constant, of course, plus an arbitrary constant. And OK, and so, but my original function was in terms of x, so I want to bring everything back in terms of x. And so I need to substitute back in, get rid of u and replace it with x. So here I just go back to what my substitution was, and I replace all my u's with it. So this is minus 1/2 sine the quantity 1 minus e to the 2x plus a constant. All right, so this is the antiderivative of this first expression here. OK, so now how about the second one? So the second one, we could also do it with a substitution. This is also a sort of a prime suspect for advanced guessing. So we see here that we have some this polynomial raised to some power. So this is 5x squared minus 1 to the 1/3. So how can we get from a derivative something like 5x squared minus 1 quantity to the 1/3? Well, if you started off with 5x squared minus 1 to the 4/3 and took a derivative, you would have this 5x squared minus 1 to the 1/3 coming out. And you would also have some stuff coming out in front by the chain rule. Well, what kind of stuff? Well, it would be some derivative of of this quadratic polynomial, which would be some linear polynomial. And indeed, that kind of matches what we have out front. So a good guess for advanced guessing is that we can look at, so d over dx of 5x squared minus 1 quantity to the 4/3. So okay, so this derivative we can compute by the chain rule. So this is 4/3 times 5x squared minus 1 to the 1/3 times, okay, so now I need to do the chain rule. I need to take the derivative of the inside. Well, that's, okay, so the minus 1 gets killed by the derivative. So 5x squared, that becomes 10x. So I can rewrite this as 40x over 3 times 5x squared minus 1 to the 1/3. So this looks very much like the thing that we were interested in, right? We were computing, where'd it go? Oh, here it is. In the thing we're trying to anti-differentiate. So the difference is just this constant out front is a little bit different. So here I have 4, whereas when I take this derivative, I had 40/3. So I need to correct for that. And the correction is just to say, oh, instead of starting with this 5x squared minus 1 to the 4/3, I need to start with some multiple of it to make the constant work out right in the end. So in this case, I was off by a multiple of 10/3, so I need to correct by multiplying through by 3/10. So we get that the antiderivative that we want, the antiderivative of 4x times the quantity 5x squared minus 1 to the 1/3 dx is equal to, well, it's equal to 3/10 of this 5x squared minus 1 to the 4/3. Okay, so that's our second antiderivative, which we got by advanced guessing. Now let's look at the third one. So the third one is tan x. Now I sort of promised you by asking this question in this section on substitution that there's, you know, some substitution that you can make. But it's not sort of obvious just from looking at tan x what should be substituted where. At least it isn't obvious to me. But one thing that can help often when you don't immediately see a substitution is to try rewriting things in equivalent ways. So sometimes you can do some algebra or some other manipulation. In this case, there's a very simple sort of rewriting that you can do, which is that tangent of x can be expressed in terms of sine and cosine of x. So we can rewrite the antiderivative of tan x dx as the integral sine x over cosine x dx. Okay, so now what do we see? So I see in the denominator a cosine of x, and then up top I have a sine x dx. So sine x dx, that's really close to the differential of cosine of x. So I'm going to try this substitution. Then I'm going to try the substitution u equals cosine x. So if I make the substitution, I get du is equal to minus sine x dx, which is, okay, so now if I plug these values in with this substitution, this integral becomes the integral, well, it's minus 1 or minus du over u. That's a nice simple antiderivative to have. So we've seen this before. So this is just a logarithm. So the minus sign comes out front. So this is minus ln of the absolute value of u plus a constant. And now we had this that u was cosine of x. So this is minus ln of the absolute value of cosine of x plus a constant. Now this should look a little bit familiar, because in one of Christine's recitations earlier, she had you compute the derivative of ln of cosine x. And in that case, you saw that that derivative was equal to minus tangent of x, just like it should be. So all right, so there we go. That was 3 examples of anti-differentiation by substitution and advanced guessing. So I'll leave you with that.